Every time the sun crests over a mountain range or a sheer wall of ice gives way to the sea, we are witnessing a massive transfer of energy. Because these shifts happen constantly and at every scale, we try to make sense of them by sorting them into categories. We separate the natural formation of a storm cloud from human-made interventions, like mining iron ore and engineering it into a suspension bridge. We measure how fast they happen. A seedling pulling nutrients from the soil to become a mature tree is a slow change over years, but touching a match to a firecracker triggers a fast change in milliseconds. We log their frequency. The Earth's rotation creates a highly predictable periodic cycle of day and night. Lightning strikes and volcanic eruptions, however, follow no schedule at all. They are entirely non-periodic. We even judge these events by their utility to us. Carefully controlling the curdling of milk to produce cheese is a desirable change. But when that same milk spoils in the afternoon heat, we label it undesirable. But categorizing a change by its speed, origin, or human utility only describes the surface-level symptoms. None of these labels actually explain why a piece of matter transforms in the first place. To understand the true mechanics of change, we have to scale down, look past macro-scale observations, and examine the microscopic rules governing atoms themselves. At this atomic scale, human labels vanish. There is no natural or artificial, no desirable or undesirable. There are only the objective, mathematical laws of physics. Here, a water molecule transitions from solid ice to liquid. The internal H2O bonds remain unbroken. This is a physical change. In a chemical change, that original structure breaks apart entirely. The atoms sever ties and snap into a completely different geometric arrangement. A physical change merely bends and flows, whereas a chemical change permanently destroys the original architecture to build something completely new. As a general rule, textbooks tell us that physical changes can be reversed, while chemical changes are permanent. But there are notable exceptions. Cracking a raw egg is a physical change you cannot undo. On the other hand, recharging a dead lithium-ion battery relies on a complex chemical reaction that successfully reverses itself every time you plug it in. Real-world behavior is dictated strictly by molecular identity. If you stir iron filings and yellow sulfur powder together in a dish, you create a physical mixture. Because no bonds have been broken or formed, the iron retains all of its individual properties. You can pull the iron right out of the powder with a simple magnet. But if you subject that exact same mixture to intense heat, the iron and sulfur atoms are forced to bond. They undergo a chemical reaction and form an entirely new structural lattice called iron sulfide. This heat-induced chemical reaction completely destroyed the iron's original identity. It permanently rewrote the material's physical capabilities, meaning if you pass a magnet over this new black solid, absolutely nothing happens. Whether matter is altering its shape or forging new bonds, every single transformation is driven by a universal thermodynamic rule. The system must balance its energy ledger, either by absorbing ambient heat or releasing heat outward. An exothermic reaction forcefully expels energy into the environment. Drop quicklime into water and it rapidly pushes heat outward. Conversely, an endothermic change pulls ambient heat in. Dissolve sugar in water and the breakdown process pulls heat out of the liquid. This continuous, strict mathematical exchange of energy is the invisible engine driving every physical and chemical shift in the universe. When a body of liquid water absorbs enough of that ambient heat, the molecules gain the kinetic energy required to break free. They turn into a gas below the boiling point, a process we call evaporation. This chart plots the environmental factors dictating evaporation speed. As lines for temperature, surface area, and wind speed trend upwards, the evaporation rate accelerates. But atmospheric moisture acts as a limit. Under high humidity, that rising evaporation rate is sharply choked off. Some materials can bypass the liquid phase altogether. Sublimation is an extreme endothermic physical change, where a solid turns directly into a gas. When solid metallic iodine crystals are exposed to intense heat, they don't melt. They instantly erupt into dense, swirling violet vapor. Whether dissolving in a glass, boiling on a stove, or sublimating into a purple cloud, matter's transition between states is entirely bound by specific, calculable environmental factors. Because this thermodynamic ledger must remain balanced, There is a fundamental law of reversal. To recover a solid from a gas or a solution, you have to execute the exact opposite energy exchange that caused the shift in the first place. Nature is completely indifferent to our labels of what is desirable or undesirable. It operates strictly by these cold mathematical laws of thermal exchange and molecular bonding. The exact same thermodynamic rules governing a pinch of sulfur in a test tube are driving the massive weather patterns shaping our continents and the heavy industrial engineering that builds our cities. Take a look at the continuous cycle of transformation happening around you: the condensation on a window, the rusting of an iron gate, the digestion of your food. Which of these changes are just passing phases, and which are quietly rewriting the physical world?